All right, so we're going to go ahead and get started where we left off. So we're working through the k-means lab, the ETL k-means, and this is going to start off. I still have part 2 up here right now just to remind what we did last, but we're going to start right at part 3. So if you had trouble with anything so far, just start with the part 3 file that's found in the labs folder, and you can run all of the cells with Shift-Enter up until part 3, and you should be in the same state that my notebook is at. Okay. So here what we did is we went ahead and set up excuse me, our k-means and actually fit it, got centers, and transformed the data set to make predictions. And if we can remember, we can see our labels and our predictions in the data frame here. Okay, so let's go ahead and let's see what actually the types of these things are and how they exist in a class structure. So we can go ahead and print out, by running this cell here, the estimator, and see that the underlying class is actually an estimator for the k-means object, but then for the k-means model, it actually comes from a model, but the pipeline itself is, oh, did I have a pipeline in here? 1 second. Yeah, so the k-means model itself, you can see, is linking down to a k-means model, which is also, there's a Java model, and below that is a pipeline model. So it's all within the model area, which is a transformer. So we can see that these are estimators on the one hand and transformers on the other, and there's a whole class hierarchy that goes down to get to these levels. So now we'll take a look at the centroids that we got again. This is what we just saved. So you should be able to run this in this command. If this doesn't work, you probably want to start with that part 3 file and start executing the code all the way up to this point. So notice that we've appended, we have predictions here for each of our labels, and we can just scroll through that as well. So the label 0, so now we have label 1. We can see it's not doing quite as well. Some of the predictions are 0, some of them are 2, but mostly we're in 2, so it seems like it's kind of naturally clustering already to our labels, which is pretty neat. All right, and then we're going to actually visualize this. So the visualizations are using matplotlib. So the Scala notebooks won't have them, but feel free to go ahead and run the answer notebook in Python if you want to actually see those visualizations or change anything in them. But I'll run just the Python notebook here. What we're doing is changing the iterations. And you can see I've done k-means a little differently this time. I actually didn't use set, I just did it in the constructor. And I'm changing the max iterations parameter as I do this looping. So that'll create a k-means model that stops at 2 iterations, 4 iterations, 7 iterations, and you can see the one that's just based on the initialization. And we've got several models here, so we can see what our center, our clusteroids actually look like. And I'm just going to print that out here. Here are our centroids. And this is just doing plot preparation, so you don't have to worry about the code here. If you're curious, you can look through here and also sort through it. So what we'll do here is we'll go ahead and get some data back, and then we'll create our plots. Let's see how big that is. I'm going to zoom out just to make this a little more clear. OK, so what's going on here? Now, in our k-means model, this is the final model where we have our clusteroid centers, and we have 3 of them, remember. So the stars actually, the yellow stars correspond to each of the 3 clusteroid centers. And I've just created kind of like a contour plot of distances going out from there. Now, the underlying, you have a red, an orange, and a gray dot. Each of those corresponds to an actual point. And the colors correspond to the original iris data set that we're working with and the target variables for those. So there's 3 classes of 3 different types of iris flower that we're looking at. And each one of those is represented by one of these dots. So we can see that that first clusteroid center on the top left is actually doing a pretty good job of clustering those red targets into that area. And there's some mixing between the natural clustering of both the orange and the gray. But both are doing actually a reasonable job here, too. So how did we get to this final model of k-means? So we can take a look through our iterations here. With 0, we can see where our random initialization was for this algorithm. So those were the original cluster centers. And then as we continue through, we can see that we've moved a little bit. So there's a gray star on the right plot, and that's representing where the old clusteroid center was. And now we've gone through another 2 iterations. How's that shifted? So this is an iterative algorithm that continues moving and then finding all of the points that would fall into that cluster, calculating a new center based on the points that are closest to it, and then it'll do that step one more time, and eventually it'll converge to a minimum. But it's going to be maybe a local minimum and not a global minimum. So you can run this algorithm with multiple initialization points, starting it off, so that you actually find a more likely to be at a global minimum. So we can see how we've continued with 4 iterations and 7 iterations, and we're getting closer to that plot that we saw originally. So here's 10 and 20. You can see the last one, even just from 10 to 20, we're getting very small movements. So the iterations, we're doing 10 more iterations, but we're only moving a little bit here. So we're really starting to converge down to a local minimum. So now how would that look if we just visualized all those cluster centroids as they move through these iterations that we did? And we can see the smaller stars and the gray ones are, as they get larger, that's how the progression occurred as this moved and tried to refit to the data and find this local minimum. And then the circles are really just showing you, it's a measure we're using as a Euclidean distance, so that's just going to be equivalent to using a circle that would go from the point. So this is just to visualize how close certain points would be, or what would represent this clusteroid versus this cluster versus another cluster. OK, so now how would we go about doing this in MLlib instead of using ML? Well, we're going to need an RDD instead of a data frame. So here I've got a little bit of code that will actually go ahead and do that. And I'm calling .rdd here, but there's no need to actually do this. There's certain operations on data frames that will return RDDs. And those are things like your map and your map partitions. I think there's a flat map, kind of standard RDD operations, which will return back an RDD instead of a data frame. And so this gets us out of the data frame world and into RDDs. So you can see what this produces. And we've just got the first 2 items in it, and we've got our tuples. The first item is going to be the label, and the second one is going to be the dense vector of the features. So we're back to that more like what we started off with, but at first we started with a labeled point and a sparse vector. So now let's go ahead and import our k-means algorithm, but this time let's do it from MLlib instead of from ML. We're just going to give it an alias here, where I'm calling it MLlib k-means, so that we can differentiate, because they actually do have the exact same name. OK, so now we'll do the same thing here. We're going to go ahead and actually set our k-means algorithm using MLlib. So you're going to have to do a little bit of a different call here. So go ahead and reference. We've got links here to both the Python and Scala APIs. And you'll see for k-means, there's a method involved here called train. And I think it's a little bit different in Scala as well. So you probably want to reference that if you're doing the Scala side. But go ahead and try and accomplish this next task, and then we'll continue on from there. Again, if you have any issues, definitely raise your hand, and we'll come around, or the TAs will come around and help out. So since this is really a single API call, I'm just going to go ahead and continue through and show you how it's done. What we do, we actually get the values out of our RDD. So this is a key value pair RDD. And so we have a label and a feature vector within this RDD. But this is an unsupervised learning algorithm, so we just need values for it. And we actually just need the feature. We don't do anything with labels at this point, but we could go ahead and look at labels later to see how we're actually doing unsupervised clustering. So we'll pass in our same parameters here that we were using before, and those just all go right into this train function. So that'll create a k-means model, and this one we're just going to give mllib so that we can differentiate it. So this is a model, again, that's returned back. We can pull out cluster centers the way that we did before. And just go ahead and look at those versus the ones that we generated in ML. And we can see we're getting the same result back, exactly the same result, which is pretty cool. And we'll just go ahead and check that. So now how do we generate predictions and compare those to our labels? Well, we can call predict. So this isn't, we're not doing a transform here, but the original ML lib libraries you typically would call a predict. So it's a little bit different, but does the same thing, except we're not appending to a data frame, we're just creating the actual predictions. So what does that look like? Well, if we run it, we see that just getting back an array. So we just have the predictions that corresponded to those input. And it's in the same order as that input that we gave it, the features that we had. But it's a little harder to look at and see what were those features and how do we compare that particular row to the prediction. So the trick here is to actually use zip on your RDD that combines two RDDs together and puts those elements from each one into a tuple. So if we do that, what do we see? And we have, OK, first thing here is the RDD from the two features RDD, which is a label and a dense vector. And then we have our prediction as another part of the tuple, so the value part of this key value pair. And the key is, again, it's actually a tuple itself. So now let's compare this to the ML. So now we have it all in one nice row. So this is one of the nice features about using ML and sticking with the data frames. You already have everything on a row-by-row basis. Our predictions have been appended. It's all right there for us to see. We don't have to go back, combine things together, and sort of do this work we're typically going to want to do anyway. And you can see the results are the same as well. So we have the same vectors with the same predictions. So the vector here corresponds, prediction corresponds. And label happens to be over here for this one. But we could reorder it too. All right, so how do these things differ? Well, if we go through the actual calling inspect on the Python code, you'll see that it really just is calling an underlying fit method. On that method, it's going to create the fit under Java method, which is going to continue on. And it's doing all the work in Java. So we might as well just look at the Scala code to see what's going to be happening here. And it's just transferring parameters and then running this. So I've produced some links here that you can follow along with. And we're going to take a quick look at the source code for k-means. And you'll see that it's actually just a wrapper in this case. This is the ML source code for how we're going to do k-means. Now, it's just wrapping mllib. So you'll see this sometimes where we're completely using the underlying libraries that already exist. Oh, so where did that go? Pull that up again. Ah, here it is. OK, cool. So fit is going to return a k-means model. So we have our data frame, because we're working in the ML space for this particular code. And we're selecting out a column. And this is the features column. So this is features call is something that was stored within this ML estimator. So we could have set features column. We could set features column to be features, or maybe give it a different name, because we've done some transformations already. And then this will go out and get the string that corresponds to that and pass it into call. And when it does that, this shortcut $sign is actually just going out and calling a get or default on a parameter. So this is a parameter that was set when we created our model. And we're able to retrieve the value from that parameter. Parameters also have default values. So if it didn't get set by us, it'll go and look for the default. And in this case, it's features. So it'll go out and get that. And then it's only selecting this one column and then doing a map operation on that column. So this uses case class matching. We're getting back a row when we do this selection and changing it into a map. So we're getting into an RDD of rows. Now, these rows you can match using Scala case matching. The point within it, which is a vector. So that vector we can just pull out. And now we have a dense or a sparse vector that corresponds to the data set that we were working with. So we've translated our data frame into an RDD of just features. And it's a RDD of feature vectors. Now we just use the mllib k-means, set the parameters, and we're getting all these back from the params that were set for ML, and create our model, and go ahead and return back the results. So you see, it's just a wrapper, but something like logistic regression is actually implemented pretty much separately from what's existing in mllib, between ML and mllib. All right, so let's go back. I've got a couple more links here if you're curious about what's going on with that $sign function and how parameters are working, if you want to dig a little deeper. And then there's also that same $sign is used, and you'll see it with Scala data frames. It actually allows you to do string interpolation, which creates back a column named, which can be used as a column. So it's just a shortcut. Instead of using call or any of these other ways of getting columns out, you can just use the $sign and do string interpolation, which works great. All right, so from here, we're going to go to the third lab, and we can pull that up. Now, all these labs are going to be on here for 3 weeks, so if you guys want to go in and download them later or review them, look at some of the links, it's all going to be available. And there is the IPython export for people that want to work in the IPython type environment as well. But that's just for the Python files, of course. All right, so next is going to be dealing with pipelines and logistic regression. So again, it's Python and Scala here. And we're going to go into, I'm going to go into the Python version. So the idea here is to introduce how pipelines work and to actually implement a pipeline where we do a logistic regression at the end. So this is using the transformers, estimators, evaluators, and pipelines in this lab. And evaluators we'll see are how we can actually get some metrics out of these predictions. But since we weren't doing a supervised learning technique before, there was not a useful metric that would apply without doing some more changing of the data. All right, so let's go ahead, get this attached. So you can see I'm reading in from the Parquet file again here, which is the Iris2 features. And this is just something that we've saved out so we can reuse it. It makes it very easy to just start at that point without having to do all the initial changing to get things into a form that we're happy with working with. All right. So I'm going to get you guys started off with an exercise here as well. And we can take a look and see what's out of this, just to remind you what we're getting back from this data frame, and that's features and label. But what we want to do is we're going to go ahead and create a function that will actually pull out from this vector the first value and the second value, and we're going to name them to be what they actually are. So there's a sepal, I think, length and sepal width that are going to come out of these. So you're going to actually write a function that takes in both the column name and a number, and that number is going to be the index of the element that you want to pull out. So it's like a feature vector, and I want the first element I'd pass in 0 because it's 0 indexed for this. So go ahead and take a shot at doing this custom UDF, and we'll wander around and check on how progress is going. And if anyone's curious about that slide deck from this morning, there is a zip file at this tiny URL, and there's also a web view where you could view. It's a Reveal.js slide deck, so it'll be in that format. You should be able to just view it once it's downloaded and unzipped on your local drive just by pulling up the local file in your, there's an index.html, and you open that up in your browser, that should load. OK, let's go ahead and go through how this example works. Now, when you create a UDF, you can have it take in one or more parameters. And these all have to be columns. So the trick here is we want to pass in a literal value. but we have to wrap it in lit so that we actually get a literal column. We turn this literal value into a column that can be used for this function. So we can't just pass the number 1 in and have that work properly. So we've wrapped, when we call the function, 0 with lit. And this is, I have to wrap it with float because, again, we're getting a numpy type back out of this vector for Python. And if I don't do this, it won't agree with the double type that's expected. So you see here, all we've done is add lit for 1 for getting the first feature out. And one of the neat things about this is we can actually register this function, too, directly into our SQL context and use SQL code calling this without having to do lit or anything. With that string, it'll actually automatically interpret it into a literal column, which will work properly in the SQL context. All right, if we go ahead and run this. So while you're running stuff, you can always take a look at the, again, what's going on. It can be interesting. Here we can see a Python batch Python evaluation is the UDF in Python that's being run here, and then some selects. But interesting to see what's actually going on in the stages. If there's multiple stages, that means that there's some shuffle step that's occurring, and information has to actually go across the network, and that can be causing something to take longer to run as well. OK, there's a built-in method for getItem that we could consider using as well, but it doesn't work for vectors, unfortunately. It'll work on arrays, and there's also a get field to get out an actual dot notation type for a nested column. Let's go ahead and see how this would work on an array. Go ahead and quickly create a data frame. So we're using rows, and when I use Python and I set a named variable here, it'll actually take that as the column name. So it's kind of a nice feature. We can do that. We can see get the first item, and look at that. We got our 1 and our 4 out of our array. So potentially you could convert to an array and then use this functionality as well. But once you're converting to an array, you're already kind of existing in that Python in this case, or you're in a UDF in one way or the other, so you might as well do all the operations there. So we'll see there's another part here. So if you had issues with that section and you didn't get it working, go ahead and open up part 2 of this file, and that'll get you started with all the solutions for the first section, and you can just run through those. OK, so we'll go ahead and do this registration I was mentioning in the SQL context. What happens if we call getElement just like SQL? Give it the sepal length and do that from our iris2. So we did a register temp table, and we called that iris2 from the iris2 features. Now that stores that within the accessible from the SQL context. And this registering also puts the getElement function into the SQL context here. We could have just passed, if we wanted to just use SQL, we could have just put in our function that would be the Python function here, instead of I'm just getting it from the existing UDF. So that's what's happening. And I'm getting the return type as well from the existing UDF. OK, so now that we've actually pulled these out, we could use another part of the data frame API to just describe the numeric columns. Now this will give us means, standard deviations, a lot of useful information for standard exploratory data analysis or just understanding the data a little bit better. So we can see we've got 150 different labels. And what's the standard deviation of those? I mean, these are just our 0, 1, 2, so that's not as interesting. But sepal length and sepal width actually have a min and a max of -1 and 1.0, which have been standardized for use in that libsvm. So there's already been some standardization around minimum and maximum. But we might want to do something different here. Maybe we want it to be normally use a normal distribution that has a mean 0 and a standard deviation of 1. And that's something we could do by using the features, feature transformers within ML. And actually, this is going to be an estimator, but we kind of call it a feature transformer because it is transforming our features. So go ahead and import that. I've got help here just as a reminder that it's a good way to get information about what you're doing. Another thing that we can do is once we've set the standard scalar, so here we're setting an input column and an output column. And we have to actually specify that we want a mean to be true. And this is kind of interesting if you think about it. Like, typically, if you're doing a standardization, you're almost always going to want to take your mean and go to 0. with traditional analysis. But let's say you have a really sparse vector, and when you go ahead and you subtract out a mean from that vector, if that mean is any different than 0, you're going to actually create different values for every element in that sparse vector. So now you've gone from having a sparse vector to a dense vector. So by default, Spark actually sets this to be false. It will calculate your standard deviation for you, but it won't calculate your mean unless you specify that you want that to happen. And then it'll take that mean and subtract it out to standardize the variables. So useful thing we can do is now that we've got this standard scalar estimator, we can go ahead and see what parameters it has. And all of our transformers and estimators are going to implement this explain params. So this will be each of the things that we can set and a little bit of information about how they work. So you'll see there's a lot of different parameters or something like a decision tree. And it's easy to just create that object, explain params, see what your default settings are if you want to change anything, and iterate from there. All right, so let's go ahead and actually fit this. Remember, this is an estimator because it has to calculate what the mean is and the standard dev is before it can go ahead and transform the data. So if we go ahead and do that, we'll do a fit and a transform on it, and we'll add a column standardized length, which is where we're pulling out of this new feature. So we're reusing that get element function that we wrote to take out one of the values, the very first value, just to look at it a little more closely. So we can see we're continuing to do the pattern of we've added another column, and we've got sepal length, sepal width, now standardized and standardized length. So very easy to look and see that everything is coming out as we would expect. So now something else that you might want to do with your data set is to normalize the data. And this comes back to that L2 norm, which we mentioned briefly, where I mentioned it more in the regularization context. But here what you want to do is you want to say, OK, I want to normalize my, say, features, and this is going to be on a row basis. So an operation like the standardization is occurring across seeing what the mean is across all of the rows. Here we're just working at a per row basis, where we want the sum of the squares of all those values to equal 1. And this could be useful if we're doing text analysis, where we have a whole bag of words model or IDF values, and we want to normalize those so that we can run k-means with a reasonable distance measure that would actually work and make sense, rather than our vectors are all of really a different length. And a way you can think of using this is kind of giving you a direction for your feature, and then you can compare those directions as vectors instead of comparing an absolute value to it. So here we're going to have another exercise. Go ahead and see if you can implement the normalizer to work with the API. It's pretty straightforward, just calling the same type of setters that we've been using. So we'll just do a little bit of time on this and then continue on. And so everyone knows we'll be doing another break at 2:30 for about 15 minutes. And then from there, we'll continue on the class straight till 5. So here we're really just using the API, setting a couple of elements. The important thing to set here is what value we want to use for P. So we're doing a L squared norm, so an L2 norm. So we're using 2 for that value, and that's what we're specifying right here. Otherwise, we're setting particular columns that we want to use, the column names that correspond to the input data frame, and what we want the output data frame to be called, the column for the output data frame. And then here we're also calling This is a transformer, so we have to call just transform on the data set rather than actually doing a fit and a transform. We can go ahead and see what that looks like. So here we're getting back the features, and they're normalized, and we can verify that this is actually working correctly. I'll just do the test. Oh. I think we're missing. Not sure what happened to that library. We're using a test helper library that we used for anyone that took the MOOC would be familiar with seeing these in the Python examples. Now we can, this is part 3, so you can go ahead and go back and load up the part 3 file if you had any issues to this point as well. I'm just going to create a custom UDF that'll calculate the norm, so we can verify that the norms look like they are 1. This is just a check against it and an example of a way to create and use a vector function within a UDF. So all this stuff is definitely, think of these labs as examples that you can reference back later for code examples, because there's a lot of this stuff isn't very well documented yet on all of the sites. So you can definitely reference these things, and it'll be useful. And hopefully we'll continue to improve the docs and make more and more examples available right through the web. You can see the feature normalization length is 1 for, or just rounding error off from 1 here. Okay, another thing we might want to do for logistic regression is we might want to take this, we'll take a feature that's continuous and actually convert it into buckets. And we'll use those buckets as part of our doing our prediction. And that's where we can use the bucketizer feature transformer that's available under ML. So it's a similar model here. The only thing we're really setting that's different is splits. One important thing to note when doing this is you really want to use the minus infinity and plus infinity. Because if you don't do that, and it might work for your test set, but you get new data in and you're training this, and you get some value that's lower or higher than what you've already seen, you're going to cause an error, and it's going to be not a fun thing to debug potentially, and it could screw up your pipeline. So we'll just go ahead and set that, and we'll do a transformation on the separate features data frame. And we see what we're getting back here. We're getting length features, which is the bucketized version of sepal length. So here, 0.05 corresponds to the second feature. This is 0 indexed. And we can see that that corresponds right in here between minus 0.5 and 0.0. And we can see a different example where 0.33 corresponds to the value between here and is indexed to between the 0 and the 0.5. So that's indexed to 2. We can go ahead and look through those and just go ahead and create another bucketizer here. What we could do is we could reuse the first one and set some of the parameters too. But since we're going to actually take this and put this into a pipeline, we're going to want to just, it's easier to create a new model, a new transformer, and then move that into the pipeline as well, and then they'll work in series. We can do all these operations together through a pipeline. You see this is doing the same thing. We got width features we can analyze. And this is more like a one-hot encoding type structure. We're now 0 indexed, 0, 1, up until the number of buckets that we've done, or 1 minus the number of buckets that we've done. So how do we combine this into a pipeline? And we want the pipeline just to perform the bucketizations. So pipeline doesn't have to end with creating a model. It can just be part of an ETL process or a EDA where we're doing some transformation of data, looking at what that transformed data looks like, not even building a model, but that could be the next part that we do after this first part of the pipeline. So pipeline, the real critical thing here is we just set stages. So we've got 2 different transformers, which are the bucketizers, the length and the width. If we set those to be the stages of the pipeline, we've created a pipeline object, doing this all together in the one line. It comes back, we can fit this to our iris separate features, and we'll get back the pipeline model. Now that pipeline model will actually do the transformation of these 2 things. Let's go ahead and do that. We'll run pipeline model transform after we've done the fit and see what we get back. All right, so here we've gotten that length features and width features all the way to that point in doing our data set transformation. And it's all handled by that one pipeline. OK, so the next thing we're going to want to do is we're going to want to assemble back. We've got 2 different features. We've got length features and width features, but we need a vector in order to take these features and use it as our, let's say, predictors in our features in our model. And they need to be in this nice vector form. So let's go ahead and do that. There's another transformer called the vector assembler, which will take multiple columns that you specify, and it'll put them into a vector. So we'll go ahead and use that. I'm doing this explain params again so we can see what we need to set for the assembler. Let's go with that up. So this is the pipeline and the assembler. And then assembler has input columns and an output column. So it's pretty straightforward. But it's calls, so it's actually going to take an array of multiple values. And it's going to output a single thing. And then the pipeline itself has stages. So with the stages, we just specify those stages. We already did it before with just the two, but we also want to include those prior stages and also the assembler. So go ahead and take a look at this and see if you can work through it, and then we'll wander around. All right, we'll continue on and see how we would solve this. The assembler has the input columns and the output columns that we need to set. And we have length features and width features were our two input columns. So we're going to set those to features bucketized. And then we're going to go ahead and do a stages. And within the stages, we'll set our length bucketizer, the width bucketizer, which is what we did before. But now we want to assemble those two things together. So we'll also add assembler to the set of stages. And then we can just do fit on the pipeline. I'm going to do both of these together on the one line. So I'm fitting the pipeline to this data frame, getting back a pipeline model, and then I'm transforming that model. Let's go ahead and see what that looks like. We've appended another column, and here's our features bucketized. All right, so here we're starting at another part again. So if you had trouble with that, feel free to start at part 4 file. And then run through the commands until you get to this point. OK, so logistic regression. Now, before on these slides, you saw there were a couple links to logistic regression, both under ML and MLlib, which are really nice descriptions of how those algorithms work and how there's differences between the two libraries. We're going to go ahead and actually create a logistic regression now. Let's go ahead and look at what our data is like. We're just going to do it as a 2-class problem rather than working on doing multi-class. So we're going to actually filter out the second. We're just going to do the 0 and 1 labels and get rid of the second label. So how do we go ahead and do that? Well, we can just use a data frame and do a filter operation on the column, specifying filter for columns less than 2, and then take a look at what grouping that up by label and counting it would look like. I'm going to order it to just by label, so it's 0 and 1 ordering. So we see now we're down to 50 of each of the 0 label and the 1 label. Well, let's create some training and test data sets. So here, I call random split. Now, random split will create it. We can do this with more than just 2 as well. I'm just passing in an array, so I could have several different elements within the array. Even if they don't sum up to 1, I believe it'll actually automatically sum things to 1 and do the appropriate percentage. So here, we're going to create 25% for our test data set, and then 75%. This is all random, but I am specifying a seed so it can be recreated. And I'm caching these things so that we'll be staying in memory because we're going to iterate on these to develop the model. We can see we got 23 items that fell into the test set and 77 that fell into the training. So now how do we go ahead and build a logistic regression model? Well, here's a couple of parameters that you need to set. And then we're going to include a pipeline this time that does everything, including the logistic regression model. Let's see here. So this will look similar to the code from before, except now we're actually doing logistic regression. We're setting regularization term here, the label column and our feature column. Remember, we created features bucketized. It wasn't just features, so it's going to default to the wrong value, so we need to specify it. Just setting iterations to be a large number here, so it'll actually probably stop before it gets that far along, because things will have converged enough. Now, when I do set stages, I'm including the assembler all the way through, and then doing LR for the linear logistic regression model. And then I'll fit that to the training data. So here, I'm fitting to just the training data. So this is where we're really seeing some of the power of a pipeline. So I want to perform the fit operation with our training data, but I want to test it out of sample on the test data. So now that I fit a model, I don't have to go through rebuilding that model, but I can use this pipeline, and that'll conform all these same translations on the transformations and then making the predictions on this test set. So it'll do all that appending of the columns and then pass those into the logistic regression model transformation, and produce predictions. So let's see what that does. We'll notice that logistic regression actually gives us several different outputs, too. So logistic regression has a probabilistic interpretation. So we can see, we'll get another column that actually has that information. So now we're starting to get quite a few columns here, but we have all of our original data, and we can look at a particular row and see how it's really being captured. So we've got our bucketized features. We've got a raw prediction. So these are the values that you're actually getting out that are then passed into the logistic function in order to get a probability. So we have a raw number that we can work with. Sometimes they're called scores. And then we have probability. And you'll see that there's two values in here. And it actually corresponds to the 0 case and the 1 case. So since we're just looking at two different cases, they're going to be mirror images of each other. Basically, on the probability, it's 1 minus the other item. And in the raw prediction, they're just negative inverse, or negative value of the other one. So we also get our prediction on this final column. Now, what it does by default is there's a threshold used with probability of 0.5. So it'll make a classification off of, is this probability greater than or less than 0.5? But you could always look at the raw score or the probability itself instead of actually looking at the prediction that comes out of it. You may want to change that threshold too, and you can set that threshold. And that'll allow you to specify based on sort of the model you're working with whether or not it's more important to be making these predictions more often or less often, or what's the balance between making a bad prediction and a good prediction. And you can set that based on that. So now that we have this model, we can go ahead and just pull out some of the data. We're going to say, here I'm pulling out the test prediction and just checking it. So this gets us through to part 5. And you can, once again, just hop into the part 5 notebook if you've had any issues with any of the code up to this point, and then follow along from here. So we've got this pipeline model. How do we go ahead and actually get some information out of it? What does our actual logistic regression model look like? Well, it's made up of stages, and with Python, I can use -1 to get the last element in a stage. So here I want to see what the weights were for my logistic regression model. So I can just run that, and it also does have an intercept, but here I'm just looking at the weights, and so this is what my basically coefficients for the model are. And those are going to be multiplied by each of these vectors that come in to produce the predictions. And those will produce raw scores, which then get converted into probabilities, and those get changed into, based on our threshold, the actual prediction. So one thing we might want to do is we've now done this bucketization, and now there's an implicit ordering because we've just set things to like the values 0 through 3. So the problem with this is that something that has a value 2 versus a value 1 is going to have twice as much impact, and maybe it's not quite what we want, and we want to allow for some nonlinear relationships or things like that. So what we can do instead is use the one-hot encoder, which will break things up into dummy variables. And that means each variable is going to have a true-false that corresponds to it. So like, does this fall within bucket 0? Yes, no. Does this fall within bucket 1? Yes, no. Continuing on. And so there's one-hot encoder does work slightly differently in Spark than I think it does in scikit-learn. There, you will get a separate dummy variable for every one of your different values that you can take on. Here, it'll compress it down to 1 less. So if something has 3 different possible states, you'll only get 2 dummy variables where one is set to 1, the first for the second state, and the other one's set to 1 for the third state. But if neither thing was set, you could consider that to be the other state. So it's a little bit redundant to do it for everything, and that's why they've compressed it slightly. So we can go ahead and run this. Same idea, we're setting just length features to length 1 hot. So this is taking the length features that we had, and we're converting those into a sparse vector here. And we can see the indice is just 1 for when length was 1. Indice is 2 over here for length features of 2, etc. So we do the same thing that we did before, and we actually create a one-hot width. So this is doing it for the width side as well, and also assemble it together. So we want to take these 2 vectors that we're creating for the one-hot encodings, combine them together into one feature vector that we can then train our model on. So now we're seeing our stages for our pipeline is getting to be a little more extensive here. We've got the one-hot length, one-hot width, assembling it all together again. What does that look like? Let's see here. We can go to our features. So the features bucketized coming out. We have two length 3 vectors here. And now those are being combined into a sparse vector of size 6, or length 6. And we can see the 1 here corresponds to the 1 value here. And then the 1 here is adding the 3 from the first one, and it's being combined in. So now indices 1 and 4 have been set. So we've captured all that information into one vector from the 2. All right, so let's go ahead, create that full pipeline. We're doing the same thing we had just done before, but we've now changed around the way in which we're doing our transformations to get a different type of variable. We can go ahead and make this as pipeline model 2 and make our predictions. Scroll over again, get our raw predictions, probability, and actual predictions again. So very easy to go ahead and add new features, change around our pipeline, run it with the different, but just run it on the test and the train sets again. So we're actually reusing those. You may want to actually separate out and do a validation set and then have a testing set that you hold out all the way till the end to really be doing your analysis in a rigorous manner. But now what does this model look like? So before we had 2 coefficients. Now we're going to have coefficients corresponding to those 6 different values that our features can take on. And we also have an intercept, which I'm pulling out here. The other model had an intercept. We just didn't print it, I don't think. OK, so now how do we test if this model is accurate or not? So we could go ahead and use some operations on a data frame and do this work ourselves. Here I'm just selecting out a column, comparing the prediction to the label that we had, and then casting these things into integers so that I can sum them up and find a mean and seeing what our predictions actually come out. This is kind of like the long-winded way of doing it because it's already built into Spark. This we could do also in SQL. Remember, we have the register attempt table, so we take our data frame, which has our test predictions on it. We register that so we can access it through SQL-like syntax, and we display those values here. So we've aggregated it up to get this 91.3% accuracy. OK, so now there's actually a bunch of evaluation metrics built into Spark itself. So we're going to use some of those metrics in order to calculate the area under the curve, and we can also do things like recall and precision as well. Oops. So this is going to be an exercise I'm going to leave to you guys. We're going to create an evaluator, and there's links here to the APIs. And what we want to see is the area under the curve for this model that we've created. So it's pretty, you create an evaluator, and then you actually call evaluate on a data set using that evaluator. And the binary classification evaluator does do the area under the rock curve evaluation for you. So go ahead and take a shot at this and wander around and see how everyone's doing. OK, so how do we go ahead and apply an evaluator? Here we'll go ahead and import the evaluator, and then specify what the raw prediction column was, and then set a metric name. Here we want the area under the rock curve, so that's just area under ROC. We can create that and then call evaluate by passing in a data set. And then within this data frame, it's going to look for that raw prediction column and use that against the label to see how we did. So we can check that on the test set, and we'll do it for the first and second models, and then just print those out. And then here I'm creating what our predictions would be for our training set, because we just had predicted for the test set. This way we can just see how we did on the training set as well for another metric. And then doing the same thing with the binary evaluator, passing in those data frames that were created. Let's go ahead and run this. So you can see it's fit much tighter to the training set than it is to the test set, which is not surprising, but this should give us some idea of generalizability when we're working on this other data set. So we've got our AUC metric, and there are a bunch of other metrics that we can use too. And there's some under the multi-class classifier if you just wanted to see precision or recall or something like that. Just compare these. Okay, now how would we actually visualize something like the ROC curve? And here I've provided you with the code to do that. Now the ROC curve really, you could think of these raw scores that you're getting back. Now if you were to specify a different threshold for raw score, you could decide at what point you want to make your predictions, and you could evaluate how many false positives and how many false positives you're getting, how many true positives you're getting, and use that information to generate a plot that has some information about how you can vary that threshold and get different, depending on what you're actually trying to accomplish and what your penalties are for failing in one way or another, you can optimize the model. And so it allows it to be done over the entire range of possible thresholds. And that gives you this aggregate metric, which is often used for binary classification, and gives you a really good sense of how accurate the model is and how you could actually go out using it if you wanted to change that threshold for your predictions. So let's go ahead and visualize that. This is just, again, in the Python code. You're not going to have this in the Scala code because I'm using matplotlib. I'll just run this. You can definitely review this code if you're interested. So here we don't have so many points that it's not a very continuous curve, but we can see that we're actually right off the bat getting most of the things right, but we have to liberalize the threshold value a bit to continue making all of the actual predictions, which then increases the false positives that we're getting. And this dotted line that runs through it is really just a representation of if this model was just completely random by chance, that's what we would expect to see. But we're doing substantially better than that. So the best thing would be an area under this curve that looks like 1.0 would be the full area. So we're doing just slightly worse. We're missing this portion in the upper left. So another thing we could do is use the multi-class classification evaluator. Here we're setting it to be precision, and we get our precision out of here. And then we could go ahead and look into that source if you're interested. There's some details for that too. So now we've been using ML for the transformers, estimators, pipelines. How would we take this data frame we have and run it through MLlib instead? Let's take a look at what columns we're working with. We have our columns here. And then we have, if we actually look at one of the rows themselves, we can see the details. So what do we need from our data frame to create a binary classification metric? And that's using the MLlib binary classification metric. So what we need to do is we need to take the raw prediction, and it wants a label. So we do, again, a map to pull that data out. And I'm doing that for both label and label 1 for the model 1 and model 2, pulling those out, and then running binary classification metrics on that. So this creates a binary classification metric like object, and we can call various of the metrics on that object itself. So here I'm going to call area under the ROC curve, and we'll do that for both of the metrics. So we get that out of there. So just another way of using, if you're doing something with the metrics that haven't been implemented in ML yet, you could always go to the MLlib library, create an RDD, pass that in, and use these objects instead. All right, now to actually build this regression model in the logistic regression model in MLlib, we need labeled points. So we encountered labeled points back with the little tour of data objects, the data types that you can use in MLlib. And now we're going to come back and take a data frame and convert it into a labeled point. So here we can see we're selecting out the label and what's our features bucketized for this example. And then we're going to take that and convert it. So we're getting a row at this point when we run map. We get data frames get turned into RDDs of rows. And then the labeled point here is going to take in that first value from the row, which is going to be the label. And then the second is going to be the features. So we go ahead and take those, cache that information, and take a look at what we have. So I did the test RDD a little bit differently. Here we're just taking out the label and the features, because that's going to be used for our metrics, so to go ahead and evaluate. With the test, we're actually just going to do, we don't do anything with the label because we're not training it. We're just using the features to create predictions. So we don't need to have it in a labeled point format. All right, so pull that out. Now here we're going to use logistic regression with LBFGS. That tends to converge faster than the stochastic gradient descent version, so it's recommended to be used. We'll go ahead and run this. So we're just doing the train, passing in the RDD, some iterations, a regularization parameter, and then we can calculate an accuracy. We could use those types that we had before. We could use the binary classification evaluator or other things to go ahead and do this. But how would we do it with an RDD itself? We actually got to go back and zip together the two values. We have the features, and then we also have the predictions. So we put those together and then see what kind of accuracy we're getting out of this model. So you see this is actually not looking like it's as accurate as the other model. So is there something that we forgot here? And in the case is, I did this without an intercept, because the default value actually doesn't include intercept for MLlib. And if you specify intercept, you'll actually find that it has the same value, because that was default to ML. All right. Cool. So at this point, we're going to go ahead and take a look at the next part. Will be actually covering decision trees. So we're just going to pull up this lab. We're going to have another break shortly, so we'll take a look at this. And I'll give you an idea of what we're going to get into, but then we'll go into that break as well. So this is 4-trees. This is going to cover a bit about decision trees, including random forests, and then also how do these decision trees actually take in, say, a target variable that has several different classes. And it's actually going to use metadata, and that's something that's happening based on using like a string indexer transformer. So we're going to go into some details on how that actually works and why we need to actually use that. And then we'll do polynomial expansion, because we're not working with that many features, before we go ahead and train a random forest on it. And we'll use cross-validation to go ahead and actually search the parameter space a bit. So we might go ahead and it's a little bit early, but I think we'll go ahead and take our 15-minute break now, and then we'll go into this when we get back. And so there's the first URL up here is for a survey for the class. So if you guys could provide some feedback. You should have also received an email with the survey. But to the extent that you have a different email address than what was listed, or you just didn't see that come through, this URL here will get you to the survey. And then the slides I also included from this morning, the links to those if you want to jot those down. So I'll just leave this up for a minute, and people can pull it up, and then we'll get back into the lab 4. All right, we're going to go ahead and get started with the decision tree lab. So here we're going to cover decision trees, random forests, also cover what metadata is used for decision trees, and then a cross-validation. And with this, we'll use the string indexer and polynomial expansion to generate more features for our random forest. So first off, let's go ahead and load that data in from our Parquet file. Get attached. So this is under 4 trees. All right, so here we're working with the iris 4 features actually pulls in a sparse vector, but we just want to create it into a dense vector for working with for this data set. So I generate a UDF that'll actually handle that. You can see we call vectors dense after converting the sparse vector to an array. I'll see how that works. A similar format to some of the other UDFs that we've put together today. And then we can go ahead and save that, because that's something we're going to use in some of the other labs as well. So we can save that down to a Parquet file. Here it's, again, you could actually save it to the temp file here if you'd want to see how that works and then list it. But this is already saved into S3 as well, so we can pull it right from our S3 bucket. All right, so let's go ahead. In this case, we're going to do a visualization of this data as well. So now we have our 4 features. So we've got petal length, petal width, sepal length, and sepal width. So we'll generate actually 2 plots with each of these side by side. So we can see sepal length versus sepal width. Again, the colors here correspond to the different type of iris flowers. And you can see there's a much stronger relationship between petal length and petal width than there is between sepal length and sepal width. But these are just the 4 features we're going to use in building these decision trees. So a way to visualize and see what's going on in this 4-dimensional space. So we'll use our random split again. Here we split into test and training data sets, doing a 30-70 split here, specifying a seed so we can reproduce this analysis. So I'm going to generate a plot here, and we can visualize how our testing sets and training sets compare. So we'll have a plot of the test set on one side, and then a plot of or the training set will be first, and then you'll have the test set as well. Let's go ahead and create this. Great. So we just happened to get 50 elements into our test set and 100 elements into our training set. All right. Let's go ahead and actually do the plot. So here we can see the training data for the sepal length and sepal width, and then how our test data compares as well. So you see these are somewhat representative of each other, and if we had a larger data set, and we were selecting more elements out, these would become more and more representative of one another. But to the extent that our test data doesn't really replicate the distribution that our training data looks like, we might not get predictions that look as accurate on that test data. Here we have it again for the other pedal length and pedal width. And we see our train data on the left and our testing data on the right. So very similar relationship there. And you've got that correlation between the two, so it's actually even easier for it to look the same with a small sample size. OK, so the first thing we need to do is actually generate, from our target variables, we've got now 3 classes. We've got 0, 1, and 2 for our classes. And we want to go ahead and pass that into a decision tree so it can build the decision tree model. So what we need to do is actually use a string indexer. And this is something I'm going to have you guys work through. It's pretty straightforward, but it's just worth thinking about what's going on with the string indexer, because if you don't use it, it's like it actually won't be able to build the model. So it's definitely an important step in dealing with a decision tree, and something you should know about what's going on behind the scenes. So go ahead and work through this one, and we'll come around and take a look if anyone has issues. So this is, again, number 4 trees, and it should be in the student version. There's no parts to this one. All right, so let's go ahead and take a look at how we would accomplish this. We import the string indexer, and then we set the column to be label and the output column to be indexed. So it's very straightforward. And then we just call fit and transform again, because this is an estimator. It has to actually run through the data set to see what we have for different target variables. So we can build up and say, oh, we've got 3 different target variables or 2 different target variables. Go ahead and run that. You can see we have a label here, but now it's being indexed to a different label. It's actually being indexed based on what occurs most frequently. So most frequent will get a label of 0, and that'll go up till 2. And we can actually pass anything in. If our labels actually were names here, instead of already being converted to numbers, which we needed for MLlib, we could just have this being the actual name of the 3 species. The string indexer will go ahead and convert those into the numbers that we need to train the model. So it's kind of a nice shortcut for that. In this case, it's doing a little bit less work. But if we called just passing the label into the decision tree, it wouldn't actually run because it's looking for some metadata that's associated. And doing this string indexer actually adds that metadata into our data frame. So as part of the check that's being done here, it's just making sure that there is, in fact, metadata associated with that. So let's see what that contains. So if we look at the second element, there actually is no metadata, but now that was our label column. So our labels did not have metadata to begin with. But now after running the string indexer, we've got the string index column. And that actually, so it's a column named index, which you can see here. And you have a machine learning attribute and the values that it takes on. And then it's a nominal type. So now we know, and we can pass to our decision tree that this is, in fact, a nominal variable that just takes on 3 different values. And from that, we can be smart about how we build our models. We don't have to pass things in as dummy variables or things like that. So typically with, you could specify a number of classes, or in some other cases, you would actually just use dummy variables to represent something that would have otherwise been represented this way. OK, so how do we build a decision tree? So it's similar to what we're doing with logistic regression. And with that, we can just bring in our decision tree classifier, set a couple of columns here. So we've got setting it to be the label as index. That's what we just did with our string indexer. And then we'll just call it max depth of 5, so a decision tree that only goes down to 5 decisions. And then max bins. Max bins, what this does actually is splits up anything that is a continuous variable into 10 different bins. So it sort of bucketizes it for you. And then we can specify an impurity here. Now, we can explain param. We saw explain params before, but we could pick an individual parameter and see what is actually going on there and get some information right from the ML libraries. So impurity tells you a little bit about what it is. It's using for information gain calculations. So when the trees are various branches, it's deciding which way to branch. It's going to use this measure or another one. There's actually only one measure for regression models. I think that's the RMSE that's currently supported. But here we could do entropy or Gini. And then max bins tells you this is how we're discretizing the continuous features, and defaults to 32, but we're using 10. So you can see what the default values are here for things, and then go ahead and change them as well if you'd like. We'll look at all of the parameters here. There's a lot of information that can be different things you can set for a decision tree, but very useful that you can see this all right here without having to go out to the API or reference things from there. OK, so how do we go ahead and fit this to the test data? Same thing we've been doing before. We're going to go do a fit and a transform here. And we could have combined this into a pipeline as well, where we do the string indexer and then we do the decision tree. But we're only having a couple things that we're doing here, so it's very straightforward to look at it step by step as well. So you can see that we're getting a raw prediction and a probability, and then the prediction that comes out of that. And this is, since we have 3 different values that our target can take on, each of these arrays has a length of 3. Well, now how do we get the results? We've seen the evaluators in place before, and now we're working with multi-class data, so we have 3 different target classes. So we'll use a multi-class evaluator to get this to work. We're going to set the metric to be precision and the label column to be indexed, because that corresponds to the way in which we're predicting. So if we use label, we wouldn't get a very good precision here. So that's coming out at 88%, it looks like. Now, this is something that actually hasn't been implemented into the Python, the PySpark aspect of ML yet. So we can actually, to get the model out, if you were to use MLlib's decision trees, you can just do a to-debug string and see what the tree looks like. But here we're going to reference the actual underlying, something that points to the Java object and call the method on that. So this isn't what you would typically be doing, but as soon as the next versions come out and this has been updated to implement this function directly in Python, you'll see this as just a to-debug string. And in Scala, you'll call it as to-debug string. So let's go ahead and print that out, and we can see what we're getting out of this model. So we've had a bunch of different decisions being made on the features. Is it less than this? Is it less than this? Predict this value. And so it's depth of 5, 19 different nodes on it. OK, so now that we have that, we can also go ahead and just replace these with the features that we know what they are to make it a lot more readable. So OK, petal length, petal width, sepal length, things that are much more intuitive to look at than to keep things at features 0 through 3. Let's take a look at that. OK, so now how do we do cross-validation? We've just gone ahead and specified a couple of parameters here, but we haven't said, OK, what if we searched over different max steps, or if we changed a couple of different things? How would we go about doing that in an automated fashion with Spark? So this is where we use cross-validator, and that takes in several different things. So what we're going to need is an estimator, and that's what will actually build out the model. There'll be an evaluator, and these are where we saw like your binary classification evaluator, where you're going to give it a metric. It's going to apply that every time it builds a model on one of the folds for the cross-validation, and then it'll come back and say, OK, this is the best model based on the cross-validation that I've done. So we need to specify the evaluator to use, and then what grid of parameters that we want to search. So if we want to search for max depth of 1, 2, 3, 4, 5, whatever it is, we'll have to specify that within a parameter grid. So in this case, we're going to use the estimator that's a pipeline, and that's going to include the string indexer and the decision tree that we had just worked on. And then multi-eval is what we're going to use, and that's multi-class evaluation, and we're using precision. And then the parameter grid builder, so when you use a parameter grid builder, you actually reference back to part of your pipeline or part of an estimator. So you can specify within the decision tree, say the max depth variable is what I'm looking at, and then give it this range of values to try and see what the predictions come out and what they look like. This is something I'll have you guys work on right now. And there is an example in the ML guide, but that is in Scala, so you'll have to translate it a little bit to Python. And then you'll have this example after. So go ahead and take a shot at this, and we'll walk around and see how everything's going. So I have a quick visualization here if anyone's not familiar with how cross-validation actually works too. So what we're doing with cross-validation, this would be 10-fold cross-validation, and we're going to split this data set into 10 pieces. So if you look at these blocks just look at the first row to begin with, and there we have 10 blocks across. Let's say the data set's been split into these 10 different equally sized partitions. Or the first one here is going to be the test set for the first time we run through cross-validation. So we'll actually train a model based on these 9 other blue values, and that's going to correspond to 90% of the data set. And then on the green value, you will have 10% of the data set, and that'll be what we've built a model on the training data, and then we actually predict it on the test data, and we get a value for that metric. And we'll go ahead and do that again on the second one, where we've now taken 90% of the data again, but we left out the second part, and that is going to be held out as the test set for this bit. And then we'll train on that and create a metric. And then at the end, we've done this 10 times. We've created 10 models. We've tested it out of sample 10 different times. So we've actually built a model on all of the data and then tested it on all of the data 10 times. And that'll give us an estimate of how we're going to perform out of sample. So that's what's going to be done within this. I think we're using 5-fold, so it'll only be 5. And then we'll create these various metrics, and we'll do this for each one of the parameters that we're looking for. So this can become an expensive operation if we're searching for 5 of one type of parameter, 10 of another type of parameter, also doing 5-fold cross-validation. You basically multiply up all those values, and that's how many different models you have to build. But it kind of becomes the only way you can really search through that space to get an idea of what's going to be your optimal model. So go ahead and continue working on the lab, and I'll come around and see if anyone needs help. So what we need to do is import the cross-validator and param grid builder, and also the pipeline. What we're going to do is we're going to first set a pipeline to include the stages for the string indexer and the decision tree. So that's going to go ahead and index everything to be, take our labeled column and create the indexed column. And that we can pass into our decision tree to go ahead and build this out. Now we can reuse that multi-eval, multi-class evaluation metric that we had and set the metric to be precision. With param grid builder, we can go ahead and add a grid to this, and we'll use decision tree.maxDepth. So it's important that we reference the actual estimator that we're using here. That's what we're going to actually change, and those values are going to be passed in. If we reference something that wasn't actually in that pipeline, we're not going to see this grid get built out correctly. So you go ahead and build this. That creates an array of the parameters that are going to be used, and so that can be used within the cross-validation framework. So for a cross-validator, we just create a cross-validator object, and then we're going to set the various things that we've established. So we have an estimator, that's our pipeline here that has the string indexer and the decision tree. And then we're going to have an evaluator, which is the multi-eval, and then estimator param maps, which is based off this parameter grid that we've just created. And for this case, we want to use 5-fold cross-validation. So we'll just go ahead and specify that here. And we then take our cross-validation pipeline, our cross-validator, and fit it to our iris train data set. So here, notice again, we're using training data. And then we're going to create some predictions off of this using our test data. And we can evaluate how this is performing on our test data set by using the multi-eval evaluate. Now, within Scala, there's actually average metrics which are created, and I think that'll be coming to the PySpark API here in a little bit. And that's useful for seeing just what average metrics happen per each one of the sets of parameters that we've passed in. So that means we can see, OK, these are my parameters, and here are my average values. So which parameters are doing well, which will help us refine the search going forward. So we could say, looks like I jumped a lot from the number of trees I wanted to create. I had 5 here, and I had 15, and I had 20. But 15 actually seemed to be doing pretty well, but 5 was doing better than that. But maybe I can actually move somewhere in between here and decide what other parts I want to search, and how can I go from where the search I've already done to improve upon it with another search. So this will create, in this case, we got the accuracy back, but it's not the accuracy that was done on the actual 5 folds. So those 5 folds are what we would really, that accuracy should be a good out-of-sample estimate as to how we're going to perform. And we'd expect to perform a little bit better than we did there because we're only training on 4 out of 5 or 80% of the data. Whereas in this case, we're actually going to go ahead and, so we're training on, and this we've split it into test and train sets already. So we're using even less of the data. And then you'd expect it, if we trained it again at the end on the full data set, the predictions are going to be a little bit better. And that's the way cross-validation will typically find your best parameter set. And then instead of training it on our 4 out of 5, 80% of the data, it'll go back and retrain the model with that set of parameters that were optimal and give you back a model that was trained on all of the data that you passed in. And we still have split this into test and train, so we then can use that on the test set. So. All right. So let's go ahead and see what was the best model that came out of this. Now, if we look at our cross-validation model, and this is really referencing the cross-validator, we get a best model attribute that we can use. And from there, we can take a look at we can take a look at the stages that were involved here, because this is going to be a pipeline model. There's still multiple things that are happening. So to access those stages, we can take a look at the last stage and then print out what this is. And this is a decision tree classification model that has a depth of 4 and 15 nodes. So it's interesting that that's the depth that really was chosen to be the optimal one. Now, we can also do, this is something that we're actually going to the Java underlying object again, because parent hasn't yet been implemented in the Python API. But from this best model, which we specified right here, we can see what the parent, and the parent is the estimator that created this model. So the estimator that created the model has these attributes to it. And these are the attributes that we looked at before in setting the decision tree, like max depth and things like that. So we go ahead and print out that entire list again and see what the default values are to go see which ones were used in building this final model. We can go down and see, we have here our max bins, and that's a current as 10, right? So we set that before. We also have max depth was default to 5, but 4 was used. So we can look through and see what really were the parameters that made the best model here. Okay. I could also just go out and say get max depth if that's the one I'm curious about and see what that was set to. So now we want to think about building a random forest. And in doing that, we want to create polynomial expansion of the feature set, because random forest is going to select just a subset of the features. And we only have a few at this point. So what we'll do is we'll take interactions between all of these variables and go ahead and generate a lot more features for a random forest to select from. So let's go ahead and go to polynomial expansion. This is another thing explained in the ml.feature API. So what this does is it takes and provides all the combinations, all the interactions. So the values squared plus any of the values times the other values. So we can see to what degree we want to do this. And for what we're doing, we are setting the degree to 2. So it's just the squared values. You could get 3-way interactions or 4-way as well. But that is quite a bit more interactions than we need for right now. So let's go ahead and build out this random classifier. So the random forest classifier, all we have to do is set it to indexed, and then now we have this feature column that's going to come out. That's the polynomial features. So we'll specify that as well. See if there's anything else that we want to set. We'll use this explain params method again, because it's very useful versus having to dig out the documentation and go through the documentation in detail. So again, we're going to see a lot of the same stuff we saw for a decision tree, but you also can set the number of trees. Setting the number of trees, typically just the more trees you have, the better you're going to do with your model. It's just going to take you longer to go ahead and train those things. And that's, random forest is not particularly set for overfitting data. With something like a GB tree, where you have gradient boosted trees, that if you continue to iterate through and run more and more iterations, you're much more likely to just be overfitting to that data set that you're using, and it's not going to necessarily generalize well. Random forest doesn't tend to have those problems. You seem to see with more trees, we get actually better results. It just takes a lot longer to train. OK, so let's go ahead and set these. We'll do max bins of 10, a max depth of just 2, and set 20 trees to be generated and give it a random. Since these are random forests, we want to set a random seed so we can reproduce this. Notice again, this is just creating a classifier. We haven't actually done anything with the data yet. We're still working in that lazy sort of setting. And then once we actually call an action on it and actually call a transformation, at the end, we'll see that it actually does do the fit and does all the work. OK, so again, a pipeline here will just include the 3 values, which is the string indexer, the polynomial expansion, and the random forest classifier. So we'll do this and see what kind of performance that we get. So we got a little improvement, it looks like, here on our, with our predictions on the test set to 94%. But what did this polynomial expansion actually do? So this is another one of our transformers that could be useful depending on what our data set looks like and what we're trying to accomplish. So here we have all of the potential interactions. So this is just using a value of 2 for polynomial expansion. And you can see, a squared, b squared down to the diagonal here. But we also have the interactions between b and A and B. And some of these are duplications. So b times A is the same as A times B. So we can go ahead and eliminate those duplications. And if we look at this here and sum up all of these plus the original features, that'll get us to what this is actually giving us as a set of features. So now the question is, we've built this model out. Is there something that we can do better with using the cross-validator to continue searching out through our space? So here, we'll do the param grid builder, giving it a grid of max depth of 2, 4, 8, and 12, also 20 trees. So here I've done something a little bit different, which is worth noting. You have a base on, and that's just specifying I want to set this parameter to be 20. And I don't want it to, so if it was set to something else before, I can just fix it for this. And it's not going to be changing it to different values like we're searching for max depth at 2, 4, 8, and 12. But here we're just saying, OK, set this to this static value. OK, now our cross-validator here, we can just set the estimator again. This is the RF pipeline, so we've changed this to a different pipeline now that we just created. Multi-eval we're still using. And then param maps is what we just created here in our param grid builder. So here I'm just going to set it to a couple of folds. Typically, you want to use more folds than this and sort of 5 and up. But just to get things to run faster here, we'll just do the 2 and move on. So once I get results from this, I can go ahead and look at my stages again, see what the parent object is and what max depth came out to be the most accurate. And that's going to be here again, a max depth of 4. There's no reason why this would be the same as the decision tree itself. It's very possible that we'd have a much deeper tree for a random forest. And with that, because we're combining up all these different random forest ones, even if some of them were sort of overfitting overall as an ensemble, we might actually be doing really well. So the 2 parameters don't necessarily actually combine. So here we have a random classifier with 20 trees. If you actually look down, you can see what all of these the variety of trees here actually looks like. But I mean, it's very extensive what this prints out to look like. So we'll skip looking at it in detail. But it is there if you wanted to actually reference what's underlying this model and what is going on. All right, so from here, I'll actually we're going to go through a little demo of using scikit-learn to go ahead and do some parallelized work over, so you're using an existing package that you may already know how to use, but within the RDD space, how do we go ahead and apply this to our, to build something that's not actually built into Spark? So we can actually do k-nearest neighbors using that. So I'll go ahead and pull that lab up. That's going to be under scikit-learn. And it's just a Python version of this because scikit-learn itself is Python. Give this 1 second. We might be overloading the Wi-Fi a little bit. So this is loading. Let's take a look at, we also have a survey that would be very helpful if everyone fills out. And that is, the link to that is right here. You should have received an email regarding this as well. So take a second to just jot this down, and you can go ahead and take a look at the survey and fill out a couple of values here. It's helpful for us to get the feedback to figure out how to change these classes for the next iteration, what would be helpful for people to know, and things like that. So if you could go to this link while I get the Wi-Fi back up here working properly. How's everyone doing on the survey? Have people completed it, or if you need more time, go ahead and raise your hand. Otherwise, I'll continue through to the scikit-learn part. OK, great. OK, so scikit-learn is going to be an example of an existing library that is in Python that we can go ahead and call right from Spark. So we can go ahead and call this from our executors or the workers that are out on these distributed systems. So these are living out, create partitions, and they go out to these executors. And then these executors can execute arbitrary Python code. So I can import the libraries from scikit-learn and run those to build models. So to the extent that the data in this case needs to fit on an executor for me to build these models, because that's the way in which a program like scikit-learn has actually been developed. It runs on a single node. So how could I think about using scikit-learn to do some of these things like grid search, which we saw under cross-validator, or we did grid search, which we saw for doing the parameter tuning, or using cross-validation. Cross-validation is also just a way to do an out-of-sample estimate. So in that case, we'd want to build these 5 or 10 different models, and we could do that all in parallel if that data would fit onto an executor. Now, we can also do sampling and then run from our various samples different models to see how those would build out, and maybe build an ensemble from those, or be looking at different types of models to see how accuracy would be when looking at parts of our data set, and do that in parallel across our system as well. So there's also a underscore student version of this that you can see. One thing with this is I probably won't pause, but if you want to code as I go along, I'll go through this, and we can just sort of add that in there. And because I know some people don't have any Python background or scikit-learn, so that might take a little bit longer with this particular example. So I'll just continue through with the example here, and you can see how to fill it in or reference back to the answers folder as well. OK, so first, we're going to go ahead and just actually pull some data in. And that's from scikit-learn has the iris data within its data sets as well. So we can actually load that data and then create test and train sets. And this is all happening right now. We're executing this in the notebook, but I haven't done anything out on the executors. So this is going to be run right on our driver program. So this is working within the driver and living there. And this is going to reference a little more RDD type work for what we're doing here, as opposed to data frames, because we're going to want to get down to the actual partition level and run things on partitions. OK, so we could take a look at a type of classifier that exists within this library. And that's a k-nearest neighbors classifier. So that's just going to look for which other points are very close to this point, and then say, oh, well, there's these 5 closest neighbors happen to be this type of species, so let's go ahead and predict this to be this species as well. So we'll go ahead and import that. And then you can just call fit within scikit-learn here on our training and test, our training data for both our x parameters, our features, and our y, our targets, and then run a predict to get the predictions out of it. Here we'll calculate an accuracy as well. So to start using part of what is really great about Spark and being able to parallelize things, we want to go in to do a grid search and say, we'll look at a few different parameters for k and see what really works the best. So I've got some links here to the actual API for scikit-learn if you're curious about just how those things work and what we're going to be calling under the hood. There is an automatic test train split that you can use within that library, and we can call that right from here. So what we'll do, we'll go ahead and import that, and then create a function for running nearest neighbors. You see that we're passing in one parameter, k, which is the number of neighbors that we want to build the model for. So maybe we want to look at the 3 or 5 or 10 closest neighbors. So we'll allow for different values to be passed in. We can load the data. It's actually available right in the package. So we can do data sets that load. And this is going to be happening on each different executor. So this is all loading all of the data on each executor. So you got to make sure that it actually fits into that executor. Now let's go ahead and split this into our training and test data using the train test. So this way we can get an out-of-sample estimate for what we're doing. And then we'll build the classifier and fit it. So we're building and fitting here. And we're calculating predictions and returning what that accuracy is. So we can say, OK, we'll pass in just the 2 nearest neighbors and find out what the accuracy is for that model, and then send that back. Or maybe it's 5 nearest neighbors or 10. So this is how we're going to do our grid search. Go ahead and put that through there. Now we can specify here, we just want k ranging from 1 to 10. So now if we range from 1 to 10, we can pass that in as an RDD. So SD parallelize actually has now this distributed set of, if we had 10 different nodes we could run this on, we could actually have one of these being on each different node. And now when we run a map on here, that's going to go out and execute this code that we've provided to it out on that node. So that's going to go out and be within the executor, it's going to run nearest neighbors. And then we can go ahead and join back those results. So we can see how the performance is doing across all these things that are being trained in parallel, 10 different models that we've built using 10 different parameters, bring those back to the driver, and then say, oh, OK, this is the one that's the most accurate. Maybe we'll use this as our actual, what we want to be using as our parameter for building the whole model. OK, so now we could also transfer this data out using a broadcast. And when using a broadcast, we'll actually not be loading it at within the data set the way we used before. So here we could load it on the driver. So the driver is that one node that's telling the executors what to do. And when we load that data in, we create a broadcast variable, which will ship it out to all the executors in an efficient fashion. So once again, this has to fit within the memory on the executors, or you're going to run into a problem with it being stored on each of them. All right, so let's go ahead and we'll go into doing that. So all we have to do here, actually, to change the code is pretty interesting. So sc.broadcast creates a broadcast variable. And then iris broadcast is the variable. .value actually goes in. Now we're accessing the value from that broadcast variable. So those are really the only bits of code that we need to change this to actually broadcasting out and using that broadcast in a parallel fashion. Now, you can notice that what's this really doing is, instead of, if I didn't do this, I just did iris broadcast here. Now, what happens is Spark has to put together this code and ship it out to actually be run on the executors. So if I didn't do that, it'll say iris broadcast is actually just referencing this other data set, which is local. Now I have to ship that out every time I want to do this. But if I use a broadcast variable, then it'll actually do it the one time. It'll live out there at the executors, and it'll not have to continually resend that data. OK, so let's go ahead and do that. We should end up with, we still have some randomness to this, so the results might look slightly different, but we're doing exactly the same technique. OK, and now let's look at cross-validation. So cross-validation is something we just saw with using Spark. We've got the evaluator there, and we can use that to see how these different folds are doing. But in this case, we can just use kfold to generate the various folds, and this is something that's built into the scikit-learn libraries. So we'll use that to generate some folds, and we can take a look at what those folds look like. So if we look at the folds here, we have, just go ahead and take the first one. And here we can see this first bit is an index into the values for this data set. And we're going to be using this whole first array as the training data. And then the second array is going to be the test data. So now we have our training data, and we've got our test data here. We can use that as indices into the data that was out on our nodes and say, OK, let's build a model up, just like we're doing under the Spark context with this cross-validator. OK, so what does, I think we just looked at this before when we were doing the cross-validator. So this is just visualizing how these different folds are working and what is our test data and what is our training data. All right, so now let's go ahead and create the nearest neighbors based on that fold information. So how do we go about doing this? I can pass in tuples that can include the training index and the test index. So these are indexing into the actual, what we're going to use to index into the actual array. So as long as we create a RDD that has these values in it, we can then call a map operation on it, pass those values along, and then run this code on our executor and be building these models in parallel. So you see, that's really the big chain is now pulling out test and train data based on these index values that we're providing. It's the same idea as to create the classifier, go ahead and fit it, and then do some predictions. Here, I'm just going to return back the number that were correct and then the total number as well, so that we can say, over this cross-validation folds, what's our complete accuracy, rather than estimating it at each part. And we'll run into some sort of like rounding errors with that. So here we'll return just the numbers, and then we can aggregate them up and get the full accuracy for how we did add a sample for that particular fold, for all of the folds actually together. So how do we do this? Now that we have our folds that are that RDD of the two different training and test indices, we can actually call run nearest neighbors on it. We just pass that into that function that we created, and we have out a tuple there. So that'll create our predictions and then come back with how we're doing. So we can see we're getting 15 out of 15 for a lot of these, 12 out of 15. We can aggregate those 10 folds back up together and see how the overall predictions went. We could use this in conjunction with the grid search, and that's something that we were doing was just the pure Spark implementation before. We're searching for both doing a grid search while using cross-validation to ensure that we're doing out-of-sample estimations with it. You can also use a train test split strategy instead of doing cross-validation within Spark. So you're doing less work to go ahead and get that done. All right, so how do we go out and aggregate the results? We can just sum up that information that we brought back to the driver. So that's all been collected back from our set of executors and workers. And now we have it locally, and we can sum it up. And I'm just going to divide the totals correct by the total number that I was looking at. All right. So now how would I go about actually sampling from a data set? Now this is a different kind of case. Like I've got too much data. It won't be able to build this model on each node itself. Instead, I'm going to have to do something about, I still want to use the single node learner and the scikit-learn package. So I might have to sample down my data. And if I sample it down, then I can actually build that model on that one node. Now, in order to do this, I can take a look at what my data set looks like right now. So first, we're going to parallelize and distribute this data across the cluster. So all we have to do here is take in the data and then tell it, we're going to get 8 partitions. I want you to actually parallelize this into 8 different parts. And then we'll take a look at what's one part look like. And we've got our label and our dense vector effectively here. It's just a NumPy array. And we can see that this is how it looks for 2 observations. Now, let's go ahead and go to the partition level. And what we're going to do is we're going to see the length of each of these data sets on the partitions. And then we're also going to look at what are the values of the labels that are stored on each of these partitions. So now what we've done is we've got 18 elements on pretty much most of the partitions, with 24 on the last one. And then we have our labels here. But you'll notice that this is an ordered data set. So our labels are actually 0 for the first couple of partitions. And then they go to become 1 and then 2. And there's some mixing of the 1s and the 2s. But we couldn't really train a model when only we have one target variable that's all 0. So it doesn't really, there's no way to differentiate in that case. All right, so what we could do is let's take a visualization of that same thing. And this will show you the class. This is target 0. And then we have the target variable 1 in the light blue and the target variable 2 in this darker blue. And so each one of these rows represents a partition. So the first partition only has those 0 variables. So you can kind of visualize what's going on with how this stuff is stored out on the cluster, where each one of these partitions is sitting on an executor sitting out there to be ready to do work. Now, you could have multiple partitions that are on an executor. So I have 8 parts, and let's say I only have 4 executors. You know, have like 2 per part. But you could certainly have them distributed as many clusters, as many nodes as you have, and distribute out that way. OK, so now that we have this, we have these homogeneous setup. How do we go about changing that? So we can go ahead and map these to add in an index that's random. And then I'm going to actually do a partitioning of that index. And that's going to cause a shuffle of all the data. So a shuffle in Spark is when we take an existing set of data on these partitions, and we have to ship it across to other workers. So this can be an expensive operation, but something that's necessary when you start to do sorting or reducing or things like that. So how do you get this information? Let's say you do like a reduce by key. You need to actually bring everything back to a particular spot where it can be aggregated together. And that requires network communication and some sorting. So here we're going to do a partition by 5, which is just actually bring this down to 5 different partitions based on this setting that we've done here with random values for 5. And return me back the values, because I don't need this. I created a tuple here. And in this tuple, it's a random value. I don't really need to retain that information. I can drop that out. So I'll just keep this other part that I had. It had the useful information in it. We'll use a couple of RDD things so we got these transformation for keys, and then actually this glom as well, goes out and gets the data from a particular partition. So you can see each of the partitions, what data is living there. So what I do is I pull that back, and I can see now like the first partition that I'm working with has zeros, ones, twos. It's got a range of different values. So this is nice. We've actually redistributed the data in a random way, and we have now a different distribution. We've got representation from each of our different classes on each of the partitions. So if we build at the partition level, that means that we can go ahead and actually build a reasonable model that's representative of the random sampling from the data. All right, so we'll go here. Let's take a look at how much ended up on each partition. You can see that in this case, we've got, it's more random, and so like the last partition actually has quite a few more observations. And we can visualize this too. In this case, the white that we're looking at here, this is where there's no data for that part, because there's a much larger number, a larger variance here. So there's no data on that part for the like third row and the fourth row later on. But we can see the different classes that have been placed into these. And we're getting a variety of each class on each of our 5 partitions. So a row corresponds to a partition here. All right. Now how would we actually go about running this? So we have to create a separate function here. And within this function, we're going to pass in the labels and features. Right? So here we've got an RDD that's stored with labels and features, like a feature vector, in this case a NumPy array. And from that, we can go ahead and build a model on a subset of the data. If we want to build that all at once, we're going to have to use a different function to pass a different transformation on an RDD to pass in the values. But we'll see what that is shortly. So here, we're just going to pull the values out of labels and features and use these targets and predictor values to go, targets and features to go ahead and make these predictions and see how we're doing on this out-of-sample performance. So again, we've used a train and test split to get an out-of-sample estimate. So if we do this, we can run map partitions. And that's the RDD transformation that's a little bit different this time. So what that's going to do is say, OK, for each partition level, give me the data, give me all the data that exists out on that partition, and pass that into the function. So now I'm able to operate at the partition level. So I've split these things up, regrouped them such that there's a nice random distribution on each of my partitions. And I can take that data, pass it into my function. Now I'm building my 10 models again on this random, or actually, what do we split it into 5. So in this case, we split it into 5. So we're running 5 different models on samples of the data on each of those executors. So we can just go ahead and take a look at how we're performing on each one of those. And we can see how much we got correct out of the total amount. So now we've managed to go out, sample by using a partitioning scheme, or we could partition in a different way. And then we can use this to also we could run cross-validation type strategies or look at a variety of different types of models and a variety of parameters, trying to get an idea of what is really working best for our data set. So how do we search this space and do it with a little bit less of our data, but do it in a parallel fashion? OK, so what we're going to do is we're going to take one last break here. And I'll put the survey information in the slide link up. So if you'd like to, if you haven't filled that out yet and you want to take a look at it, we'll have a 15-minute break and we'll come back. There's a variety of other labs I have based on the Wikipedia data. So I also give an overview of everything else that exists in the lab folder so you guys can review that material. And then we'll have everyone work on a lab, pick a lab that you're interested in, and start working through it, because there's a few other examples. And whatever interests you the most, we'll go around and we'll answer questions on that. I'll probably actually start off right after the break with a more open Q&A. So whatever questions you guys have, we'll go through and discuss those. And then we'll go through the labs so that you can explore something that's most interesting to you. All right, so let's go ahead and take that break. All right, we're going to go ahead and move into a period where we do a little bit of Q&A. After the Q&A, we'll go from that to, I'll explain, there's a series of other labs. There's a few on Wikipedia data. And there are a couple with the numbers 5 and 6, a regression and a sampling lab, really just demonstrate some of these different techniques. So I'll explain what's in each of those, and then you guys can pick which one you want to look at. And we'll wander around helping out with any questions that come up or explaining in more detail specific questions that you guys have after this part. All right, so if anyone has any questions, also Stefan, who's helping out, has the microphone, so he can bring that to you, and you can feel free to ask anything related to this material we've been covering here. So just raise your hand if you do have a question. Here, there's one there.
Hi. I was wondering if you could go into a little more detail about the relationship between MLlib, ML, RDD, and data frames. We kind of touched on it, but it's sort of a jumble for me now. So I was just wondering if you could talk about that a bit more.
Yeah, so the MLlib libraries work on RDDs, and since data frames came after that library was initially formed, you'll find that all those operations are working directly on RDDs, and you have to do things like zip together your results from your predictions that come out of MLlib. Now, ML since data frames has become the sort of major way that development is working, and Spark SQL has really been this major undertaking to get data frames to be really efficient and leverage Project Tungsten, which has a binary format for storing data, but it really requires a schema to be associated with it to be able to do this efficiently. And so that's where data frames works, and we're able to store a lot of information, keeping it out of garbage collection where you have so many objects, where with an RDD you could potentially run into issues that the JVM, especially with a large executor, is going to have to do garbage collection pauses, which could cause it to seem like it's actually not up running anymore, and the driver could disconnect from it. So this is part of the impetus behind why we have the data frames. And then since that's where a lot of optimization is going into it with Catalyst and these other strategies, it's a more efficient way to do a lot of these operations. So we're trying to move all the other libraries to use data frames as much as possible to get these benefits from these optimizations. So MLlib has a preset API, and it needs to be continued to be supported. And so that's not going to be updated to use the data frames directly. But we have ML, which has become the library that uses the data frames. And so that's gaining feature parity right now with MLlib. And I think you'll see that's going to be more of the focus going forward, just because the data frames is the focus at this point. Any other questions? Oh, back there.
Yeah, it's about the Scala versus Python. I mean, for some time, Scala was richer for Spark, but with the integration of more and more features in Python, actually Python turns out to have lots of stuff that are handier. So I'm wondering about your strategy to actually, in what direction you go for having those features going from Scala to Python or conversely.
So do you say what should a user be looking at using for language, or how does the decision to add functionality occur to the various APIs?
So basically, it's as a data scientist, you have to make a choice on the language.
Yep.
Still now. It's difficult to go from one to the other seamlessly. And so it's basically the strategy for a new project will depend on the various of expectations on the project to choose the language. And I was wondering if what you were planning on doing, pushing more Python, still building from Scala and then migrating to Python, or these kind of things.
Yeah, I mean, if you already are particularly comfortable with one language versus the other, I mean, I recommend sticking with it. And there are things you can do, like trying to do PyPy to speed things up for Python. Or you can try and work with actually optimizing the Python code if you're having bottlenecks around that stuff. To the extent that you haven't sort of pre-decided on a language, I'd recommend going with Scala, just because it is the language that the core is written in. And so you don't have to deal with using the Python process and sending information out to it. So you're going to get some more performance there. But to the extent that it's really more data science time, that the time of your data scientist that matters. So if they already know Python, I would say just go with that. and don't bother retooling to Scala, unless you run into a real performance issue. At that point, you might think about, like, OK, do I need to move this code? Or maybe there's something I can do in the Python side of things to make it faster as well. Yeah.
OK, thanks.
Mm-hmm.
Say if you have some kind of custom model calculation, is it easy to create that in Spark as well to make it parallelizable? If that makes sense.
Is that to build a new type of model, or to, you're saying you have an evaluation metric that you'd want to use for how to train, like let's say you did cross-validation, and you wanted to use that as a custom evaluator for which model to select? Which of those?
More the first.
The first. Yeah, it really depends on the model you're trying to do. I mean, it's not trivial to change certain models over, because like, so you're working with a matrix-based model, you have to go to an optimization type strategy, and then figure out like what your gradients are, your first derivative, maybe second like derivative, depending on how you want to build it. And then how do you deal with communication? So they're inherently somewhat difficult algorithms to build. But if it's really, is it worthwhile to invest the time and resources on it, or is anyone else working on it too? I'd certainly check. There's a Spark packages that has some packages that people are working on. They might not be things that are going to be incorporated directly into the core, into these MLlib libraries or ML libraries, but it might have the functionality you're already looking for there too. Or you could use some of those techniques where you reuse existing code, but you're not going to get that scale with it because you're using an existing library that's a single node solver kind of a library. But it's definitely not a trivial task to port something over to a parallelized system like this.
Okay, cool. Thanks.
Yeah. Have any more? Very cool.
Are you aware of any plans to adopt any other type of methods for cross-validation, type of Monte Carlo and things like that? Is there in the pipeline, I mean, any plans or anyone working on that?
Sorry, could you repeat that?
Monte Carlo type of approach, rather k-fold on cross-validation?
Is there another, besides the cross-validation, is there another?
Yeah, it's different from k-fold, so different approach, using a Monte Carlo type of a stress test and all these things.
So there's just now there's the cross-validator, which does the k-fold, and then there's also the test train split, which just does the splitting it into two pieces rather than doing more folds or anything like that. That's all that's currently in there.
Sure.
I mean, you certainly could write your own library too if you had a different strategy for how you wanted to approach it and plug that into Spark. I don't know of anything that's currently on the pipeline for going right into ML to do a different strategy. I think those are the most common ones you see. And they model a lot of this off of what exists within like scikit-learn as a library too, and trying to get parity with the transformers and things that exist there. So that's definitely a good guideline for how the thought process is working.
Cool. Thank you.
For the labs, in the Python version, there were some graphs using matplotlib, whereas in the Scala version, there was no plots. Are you aware of any libraries that can be used for plotting with Scala?
I'm not familiar with the Scala plotting libraries. I mean, if you're familiar with anything in Java, you could definitely link that in too. I just know matplotlib is very easy to do these visualizations with, so that's what we went with. I mean, you could always save your data to a data frame or a table and then load that into a little bit of Python code and run that visualization in a separate notebook. And that might be a strategy to employ. But if anyone has any great visualization libraries in Scala, I'd definitely like to hear about them. But I don't know. Yeah.
And what about R? I mean, Python is becoming a very used language and you are investing on it, and you showed a lot of examples and the use of scikit-learn as a library, but do you think the future will be focused on Python, or that there will be the same improvements also for our language?
So currently, the Spark R, the focus is on getting it to where you can call all of the existing ML and the ML libraries and use all the functionality that exists within data frames and things like that, really as a wrapper to what's the Scala code that exists in Spark and what can be done there. The current plan is to support Python and Scala and Java as the main languages you can do anything with. You can write a function in and pass that function along to the executors to run there, load libraries and things like that. Currently, I haven't heard of any plans to make R more a general purpose language like those languages, and we'll have to see if there's enough interest to push that forward. But right now, that's not the focus. It's getting its kind of feature parity with just using what's existing in Scala and in the libraries that are there. Cool. All right, well, I'll go ahead and explain the couple of the other labs that we have here. If people have interest in different techniques that are going to be explained in those, you can go ahead and work through those labs. And then I'll come around, and if you have individual questions, we can just address those one-on-one too, or questions about the labs. So I'll pull up the lab folder. OK, so we got through the first 4 labs in here. And then there's also a lab on regression. So this is just doing a linear regression model, but it's generating several of them using bootstrap sampling. So the idea here would be, when you run these optimization primitives and you do things like stochastic gradient descent or you do LBFGS, you're not doing the way in which statistics is typically done, and you have a matrix, and you actually do the matrix computations and get a bunch of values that you can later use for, these are the standard errors of my coefficients, or I want to say this is my F-test on this thing. So one of the things you can do is you can generate random samples and do boosting, and use that to generate a bunch of different models and see how your coefficients actually change. That's going to be an expensive process, but it's one way if you're really concerned about how do I move from this more traditional statistical analysis into this world of optimization, and someone still really wants a t-score or a value like that, how would I go about calculating that? And that lab kind of goes through and demonstrates some of those techniques. The sampling lab here, this is just a couple of overviews of doing a stratified sample and doing a sampling, a completely random sample. So something you might commonly want to do with data science techniques. Now the MOOC, this would be from the Scalable Machine Learning MOOC that was offered recently. The 2 labs are in here. One's gradient descent. These are both in Python. Other stuff is actually in Scala as well, but the MOOCs are just currently in Python. So you can take a look at the one lab is going to be, I'll pull it up here. Oops. So it's going to be under gradient descent, and then that's going to be actually writing your own gradient descent model or algorithm, and you'll run it on a data set. And then the other one is PCA, where you actually do PCA, which is an interesting example of an algorithm that is in between a very large, being able to work with a very large data set and a smaller data set. So this is a strategy that you could use if you have a really massive amount of rows, but you don't have too many columns. And so you can actually do some matrix math based on outer products, and that goes through detail on that. And those have exercises and everything from the MOOC that was offered. Then you could go through the scikit-learn one, actually trying to implement it yourself. There is a student fill-in section there if you wanted to try and see how that more RDD type operations work and how you'd parallelize things using a strategy like that. We have LDA. So this is going to be an unsupervised technique. This lab is only in Scala. But if you take a look at it, it's interesting. It's a way to do topic modeling across the Wikipedia data. So how do I classify these models, classify these documents at the document level into, say, I want 10 different topics, and then each of these ones is going to have a distribution around those topics. So it might be 80% topic 1 or 20%. It'll have a association with the 10 topics, so it's not just going to be classified into one of the 10 topics. And it's an interesting way to go ahead and create a vector around text. So you have this unstructured text, and now I've created a topic feature vector that could be used in future models where I'm trying to do some sort of specific supervised learning technique. After that, there's the term frequency, inverse document frequency, which goes into a k-means model. This is really more like another example of a pipeline. And we're going to use this where we do the normalizer, which we spoke about before. And that's going to take the word counts and actually normalize those so that we can do a k-means distance measure on them using Euclidean distance. And then there's a word-to-vec example. And that's creating a vector for each word that occurs with a certain frequency within the set of documents. And we break things into sentences. So you'll see the Wikipedia data is actually separated into sentences. And then those are sent in and be trained within word-to-vec to generate a vector around each word. And using those vectors, you can compare documents or words. And you could use that outside of the Wikipedia data set for something where you have text classification problem. And you want to generate a vector that can be compared against another vector, but you've got words. So if you just compared the words themselves, there's not necessarily a logical way to do, one word versus another. But these words should associate vectors that are close in space together. So that one will demonstrate that as well. And that's really the overview of the labs that are in here. So I'd recommend that what you do is you pick one that sounds like something that's a little more interesting, something you'd more like to dive into. You really have pipelines within the TF-IDF one, and you get into some more of these other ML techniques in the other ones. Or you can do more of a MOOC-based approach and try and write your own gradient descent or PCA. So if you guys want to go ahead and get started on that, I'll come around and answer any individual questions related to the labs. Or if you have stuff that's just general questions too, feel free to ask that.